morning, everyone. This is Justin Ferry from AMJ Consulting on behalf of the I-95 Corridor Coalition. I'd like to welcome you to the Volume and Turning Movements Project Steering Committee meeting number 8. We have a couple of great speakers today, and we're excited to begin. Just for some housekeeping items, that is my cell phone number. Feel free to call me if you have any web or audio issues. And keeping in line with our webinar series, this is a virtual meeting experience. So make sure that unless you're asking a question, you have your phone line muted. You can mute from your headset or press *6 to mute and unmute. Speakers will answer questions at the end of their presentation. The audio from this meeting is being recorded, and all materials and contact information will be available to participants after the webcast. With that, I'd like to turn it over to Denise Markow. Good morning, Denise.
Thanks, Justin. Good morning, everyone. And just as an FYI, Justin will also type his cell phone number into the chat box in case anybody does have an audio or web issue. But thank you all for joining today. Listed in front of you are the attendees from some of the agencies and organizations that we've had, not just today, but consistently over the past 7 steering committee meetings. So there's about 16 agencies, some of our probe data vendors, and Federal Highway. We welcome you all to this steering committee meeting number 8. So today, the speakers we have, most of you know Stan Young, who will be presenting information from NREL and the data work they've been doing there. Kaveh Sadabade is the principal investigator from the University of Maryland. He works with Zach Vander. And today, Zach is going to be stepping in for Kaveh, who has a family issue, and I know we're in good hands, but he will be presenting to you some of the updated results they've seen from the New Hampshire and the Florida data sets. So those are the speakers we've got. Again, if I could please confirm with all of you guys to mute your lines. When we have larger webinars, we tend to bring the attendees in as muted, and they have to type in the chat box. Being a smaller group like this, and we really want you to be able to ask questions or to chime in as needed, we've allowed that opportunity. So you have that ability to just talk or ask a question at will. So in order to keep everything really quiet, though, for the speakers, we do ask that you mute your line. So, sorry, Justin. The agenda. Stan is going to be providing a project status update for everyone. We're going to move then to Zach, who's going to talk about the work they've been doing with Florida and New Hampshire, as I mentioned earlier. The topics will then go back to Stan, who's going to be talking about some of the error analysis that they've done with the VTM project. And then we're going to follow it up and finish it up with some future work and what our next steps are. So with that being said, I'd like to turn this over to Stan.
Thank you, Denise. Is the audio coming through well? Kind of a sound check here.
Yeah.
Good. Okay. Well, I get to warm up the crowd a little bit before our main presenter from UMD. Everyone, I'm looking at everyone that's logged in as participants. I think half of you we've had conversations with either one-on-one or at conferences. The other half maybe hasn't seen this material since our last steering committee several months ago. So I got a few slides just to bring everyone up to the same level before we turn it over to Zach Vander to present the University of Maryland material. Kind of a background material, why are we pursuing volume estimates through probe data. We need more and better volume in operations. We need better real-time. I'm getting an echo on my line. I'm going to pause to make sure everybody's muted. I'm hearing my own echo, which is a little bit causing me to stutter. Could we do a check to get that turned off? Okay, we'll try this again. For the operations, in the real time, we need better real-time presence of what's going on, particularly for inclement weather and special events, seeing those unusual traffic events and what it's doing to the volume patterns on the network. Performance measures, this is the one that really brought it to our attention 3 or 4 years ago when we were doing some work at University of Maryland calculating performance measures all places and at all times, and the volume data we had was just average from HPMS at the time and ended up causing quite a bit of problems. We were using nominal traffic volumes during the middle of blizzards, and that doesn't work very well. And lastly, economic and energy assessment. I've been working with the DOE for the last 3 years, and it's coming to the realization that the volume measures that we have serves many other purposes outside of strictly transportation operations and planning, and one of them is in the energy domain. And so providing better volume estimates will feed a lot of areas, particularly the energy interests that I'm working with now. What we're trying to do, we call it ubiquitous traffic volumes, is one of the nicknames that it goes by. I show 2 charts. These charts are from some of the work we've done at the Colorado, particularly Denver regional area. On the left, all those blue bubbles in the Denver metropolitan regions represents the continuous count stations. These are the areas that we have high confidence counters. There are definitely more sensors than that out there. These are the ones that are maintained well in terms of having calibration validation frequently. But there's only 14 of them in the whole metropolitan area. And through using the high confidence data, combining it with other data sets, one of the most important ones being probe data, we're hoping to create a map on the right which shows volumes anywhere, anytime, across the whole network. And this just shows it for freeways. We're doing it more than just freeways. We're trying to light it up for off freeways as well, going down the functional class as far as we can. The proposed solution, I use this diagram frequently. It's a very top-level diagram to show how it works. You may be aware there's 2 teams working on this, a team at University of Maryland and a team here at the National Renewable Energy Lab. This diagram works with both. We're using a very similar processes that look the same. On the input side, we use quite a bit of inputs. Probe traffic data is at the top. These are the travel times and speed, as many of you already have, but it also includes probe traffic counts, how many probes the vendor sees on any particular segment at any particular time. But it's not the only data. We put in road characteristics, such as the number of lanes. We put in weather information to indicate, particularly it gives us clue on inclement weather conditions and how those patterns might change, and also temporal information, time of day, day of week, things like that. Many of the nominal traffic volume patterns are quite repetitive and helps inform. All this goes into an estimator. We have to calibrate this estimator. This calibration comes from data from our high confidence sensors. These are typically highway performance monitoring sensors, but they don't have to be. Any sensor network that's maintained well and has a lot of confidence can help calibrate it. And then we create output. This estimator is typically built on modern machine learning techniques, whether that's tree learning techniques or neural networks. Those are the things we've been working with in our research team. And then we get output, and the output is volumes for any hour of the day, anywhere on the network, both real-time and historic. Now, what we've done up to now is show proof of concept. All our proof of concept work has been primarily on historic, mainly because we don't have the data inputs in real time. But this basic proposed solution, as far as how it works and the mechanics, is adaptable in both regimes. One of the big emphasis areas in our project is to try to answer the question, how good is good enough? So we're looking forward to the next round of the Vehicle Pro project, where we can begin to merge some of these volume estimate engines into the normal probe data, and trying to look forward to putting specifications around there so we can validate towards them. We have 3 that we use frequently. That's not the only 3, but 3 good metrics that we're trying to put a lot of thought in. One is mean absolute percentage error. Typically, this is in the traffic engineering domain. The expectation of accuracy is really volume dependent on freeways. We'd like to see that in the 10 to 15% range, and as you go down into the various road classes, all the way down to the very low volume roads, the expectation of accuracy expands appropriately. We put a little example from the Minnesota DOT. They've been interested in this and has run 1 or 2 research studies, and it shows their acceptable range of accuracy, particularly in the low volume road range. They've been working on areas of how to find different ways to get accurate estimates of AADT on their system without having to send out crews on their low-volume roads. If you're a planner or a statistician, the R-squared coefficient of determination is kind of the metric of choice, and we put it there: 70's good, 80's better, 90's best. We'd really like to see it 90 and above whenever we can. Highway operations, we use a term called error to capacity ratio. And if you can't estimate capacity, error to maximum flow ratio. This is one where, tell me the error relative to when traffic begins to break down. That tends to be where highway operations is most interested. We did some survey work, and they said if you can't get it less than 10%, probably not useful, and the target is really 5% or less. So in all these domains and dimensions, we try to present our results and try to build it forward to the time when we have this built into a standard data feed. That's kind of the warm-up. We'll come back at the end and let you know what we're working to next, but at this time I'll turn it over to University of Maryland. Zach Vander is going to be presenting their material that they've been doing in Florida and New Hampshire. Zach, are you online?
Yeah, I am. Thank you, Stan, and good morning, everyone. As Stan said, I'm going to be providing the update from the UMD perspective. I'm talking a bit about the work we've been doing recently in Florida and New Hampshire. So here's a brief outline of some of the things I'll talk about today. Stan did a really good job of providing the volume estimation framework. I'm just going to present very quickly, one or two slides on how we like to talk about it based on what we're doing at UMD. And then I'll jump right into the results from Florida and New Hampshire analyses. Now, if you recall, in the last steering committee meeting, CATT presented some initial results from our Florida analysis. And so I'll show a few slides that may look familiar. But since then, we've gone beyond this initial work in Florida, and we've done some work with AADT estimation, freight volume estimation, and some other work as well with flagging unusual behavior. Then we moved to a different data set, to New Hampshire, and we've been repeating some of these same processes, trying to understand how the errors and the model quality compares in a different state. But one thing I want to highlight is that with respect to New Hampshire, we've been exploring this idea of model transferability. So can we leverage some of the data and the model that we've developed in Florida to help improve volume estimation work in another state, perhaps one with less data. So those are kind of the main topics I'm going to be covering in the next few minutes. So again, we have this, just to reiterate what Stan said, we have sparsely located continuous count stations which have high fidelity data, which is great, but we'd like to know the traffic volumes everywhere on the network. And so the idea is we want to leverage this probe data, which represents a small fraction of the actual vehicles on the road. We want to try and scale this up by using these probe counts and other archived data and feeding these into a model which ingests the data and then produces as an output volume estimates everywhere on the road network. And the way we like to talk about the approach we take is separating it into two steps. And so in the first step, we focus on developing and training the model. And really, this is where most of the work is focused. In this step, we look only at the locations where we have high-quality ground truth data. So these continuous count volumes. And at these locations, we know the ground truth volumes. So we extract all this input data. We take our input variables, such as the GPS probe data and speeds and other information, and we teach our model or calibrate it to learn the relation between those inputs and the actual ground truth volumes. And then once we've done that, we can move to the second stage, where we take it and then apply it everywhere throughout the network. And again, this is the ultimate goal, to light up this whole network with hourly volume estimates every hour of the day, everywhere on the network. So I'll start by quickly going through some initial Florida results and then spend a little bit more time on some new additions to this analysis. So again, the data that we're using here, this slide says Florida data set, but really the data inputs are the same whether you're conducting an analysis in Florida or New Hampshire or Maryland or Colorado. This process is pretty similar everywhere. But if we look at the left-hand side of this slide, these are the model inputs that we're using. We have them listed out here, but again, I want to emphasize that the key ingredient is this GPS probe data, both the speed and the reported probe speeds, and also the probe counts. In our case, we have to do a little bit of pre-processing of this data, which we obtain from NREL, and this is a very large data set in Florida. It consists of 75 million trips coming from 3.4 billion GPS waypoints. And so we have to do a bit of pre-processing to turn it into the counts, which we use as an input to our model. But again, this is this probe data is the key ingredient, and this comes from a small sample of actual vehicles on the road. From our initial experiments, we found that the fraction of probe vehicles to actual vehicles on the road differs spatially and temporally as well, but when we talk in terms of typical or median penetration rate, we're looking at somewhere around 2%. Then again, so the left-hand side of the slide is looking at all of our model inputs. On the right-hand side, I just want to emphasize that we also need this high-quality ground truth data, both for training or calibrating the model, but then also for evaluating it to test how well it performs under a variety of conditions. So if we recall, this first step I described involves training or calibrating the model to learn the relation between the input variables and the actual ground truth volumes. So the model we chose to do this is a type of artificial neural network, which is a machine learning model that is capable of learning these complex nonlinear patterns. And so once we calibrated a model, once we decided on the input variables, which I've already shared, and we decided on a model architecture, we then train or calibrate it. But before we decide that it's okay and that we want to expand it to the entire statewide network, we need to do a process called cross-validation or repeated cross-validation. And this is something that we've walked through in more detail on previous steering committee meetings. But essentially, at a high level, what we're trying to do is make sure that our model's not cheating. We want to train or calibrate our model on part of the data set and then test it on a different part so that we can simulate how our model would behave when we take it away from locations where we can verify it. So we want to make sure that our model can generalize to scenarios that were not used in its calibration. So once we've gone through this cross-validation process, at this point we have actual traffic volumes for every hour at each of these locations, and we have our actual volumes and we have our volume estimates, and then we can compare these to see how well the model's performing. As a first stab, we can look at things visually. So if you look at the right-hand side of the screen, this is plotting the actual volumes against the volume estimates at the hourly level. Now, if all of our estimates were perfect, they would fall on the 45-degree line. And of course, no model is ever going to be perfect, but we're encouraged to see that most of these estimates form a reasonably tight band about that 45-degree line. So that seems to suggest that there aren't strong biases, that the model is generally performing pretty well. But as Stan mentioned, it's important to also quantify the model performance in terms of some standard error metrics. And so this slide here kind of summarizes the model performance in terms of the R squared, mean absolute percentage error, and error to max flow ratio. And so I'm not going to walk through all of the information here, but something I want to point out is that we tried to tease out the results in terms of different scenarios too. So while we do report the overall median error metrics, which are on the upper left of the slide, we also want to see how does it perform on different functional road classes when traffic has different hourly volume levels, when we see more or less of the GPS probe data. And so we want to try and glean some insights from this. This slide was actually shared in the previous meeting, so I'm not going to go through it in detail, but I just want to point out that in addition to our overall typical or median performance being quite good, based on the slide Stan shared about how good is good enough, other observations are that once you get onto higher functional road classes, on higher volume roads, as you see more of this key ingredient or the input GPS data, the accuracy is even higher. So once you finish this first step in the process, this model calibration and evaluating its performance, you kind of iterate through this whole process of developing a model. Once you're finally satisfied with that model, we can finally move to the next step of applying it everywhere on the road network. And this again is our ultimate goal. So conceptually, this is very simple. Once you have a trained model, you just need to feed the model the inputs, and now you can generate volume estimates anywhere. It turns out that it's the challenge for this step in the process is more of a data challenge. Wrangling all the data to obtain the necessary inputs at over 20,000 locations for every hour of the day is a bit of a challenge, but once you do that, then you can generate these hourly volume estimates. Now I hope you can see this animation right now. Is this playing?
Yes.
Okay, great. Yeah, so this is a little time-lapse animation just to show it's helpful to conceptualize what these hourly volumes look like. At each instant in time, we can color the entire TMC road network, and then this animation is just iterating through the hourly intervals. So then, another thing that's useful sometimes is to zoom into, to a major metro area and try to understand what's happening there in a bit more detail. When you do this, you can see exactly how certain road segments are lighting up. In general, the results look consistent with what we would expect. Also on the left, you can see there's time series plots showing the actual and estimated or predicted volumes over the course of a few sample days, just to help build an intuition for what these results look like. So one of the things as we were developing this approach, some of the feedback we got was that it would be really useful to be able to estimate annual average daily traffic as well. And this is a much more aggregate metric than with a different focus than this highly granular hourly volume estimation approach we've been taking. But nonetheless, we decided to explore its feasibility. So we took basically the same approach and first estimated hourly volumes and then rolled those up to the AADT level and compared those estimates with ground truth values and then recalculated error metrics. And we found that the accuracy is quite high. And so if you look at the error measures as compared to our hourly volume estimates, they're even higher. So this is encouraging, suggesting that this approach is is a viable way to estimate AEDT, and potentially a very efficient way to do it. Another area of research that we've been exploring is whether we could take this existing approach and use it to also estimate freight volumes. There's a lot of applications for that. And so the way we tested this is we went back, and rather than training the model to using the continuous count station data from all vehicles, we went back and recalibrated it only using the freight volumes. And we did it once for all trucks using FHWA weight classes 5 through 13, and then we did it again only for heavy trucks using classes 7 through 13. And then went through this entire process and tried to quantify the model performance. And so the takeaways from this are that if we look only at the highest functional road class, so if we look at these tables recording the overall median performance and then the median performance on different functional road classes, the performance on the highest functional road class is very similar to the accuracy levels that we're seeing with the overall model. So that's very encouraging. Now, as you go on to some of the lower functional road classes, the accuracy is quite a bit worse than we had initially seen. And the problem here is that we just don't have very many observations of trucks, and particularly heavy trucks, on these low functional road classes. And so the takeaway here is that this approach looks promising, particularly if we can acquire enough data. Perhaps if we were able to get a full year's worth of data, we'd get some more observations on the lower functional road classes. And either way, the freight estimates on the higher functional road classes are particularly relevant and useful. So this is an exciting area of research as well. And so one more thing I want to point out before leaving the Florida data set is that we've been giving some thought about how to make these volume estimates more useful for the end user. And so one thing we were thinking is that it would be helpful to alert the user who might utilize our volume estimates to when something abnormal is happening, either in terms of the input data or the estimates that we're producing. So we've been working on developing some flags to highlight this. Right now, we've developed two. One of them looks at this, the GPS probe data, which again is our key model ingredient, and we're setting a flag to indicate whether it's in a typical range in terms of the number of counts you observe on that road segment during the same day of the week and hour. So seeing whether those the input data you're seeing is typical or whether it's significantly higher or lower. We're also doing that in terms of our model estimates, and the value of this, might be alerting the end user to an accident or something that happened where the volume is very different than what you would expect at that day of the week and hour of the day. Okay, so now I'm going to move to the New Hampshire data set, which also is from 3 months, like the Florida data set was. But the key difference between New Hampshire and Florida primarily lies in the size of the data set. So if you look at the right-hand side of the screen, we've kept some of the statistics from the GPS probe data from Florida, and you can compare that against what we're seeing in New Hampshire. And so the New Hampshire probe data, the data set is much smaller. It's much smaller than what we see in Florida. And the challenge with this is we weren't sure as we were working on the model development whether we had enough data for our model to be able to learn these patterns between the observed volumes and the input data. So So something I want to talk about before I share the results is this idea of transfer learning. So based on this idea that I just shared, we wondered whether we could leverage this rich data set that exists in Florida. That is, could we take either the model itself that we developed in Florida and apply it in New Hampshire, or could we at least take some of the continuous count data and input data that we had extracted and use that to train a better model in New Hampshire. So in order to test this, we went through 4 scenarios, and I'll just explain them briefly here. They're listed in the table on the screen. So the first one is called Florida, and what we did here, in each of these models, we're testing the model performance in the state of New Hampshire. But for the first test, we took the model that we had already trained in Florida and brought it to New Hampshire and saw how well it did with no modifications. Next, the model called base, we ignored this idea of model transfer and only trained the model on New Hampshire data. So we didn't use any of the Florida data there. Then the next one, called transfer learning, we took the existing model that we had developed in Florida, kept it mostly intact, but did allow some of the parameters to be adjusted in light of what we had seen in New Hampshire. So we did introduce the New Hampshire data as well and allowed this existing model, which was mostly kept intact, to be slightly modified. And then finally, the last one, called extended, we took all of the Florida data and the New Hampshire data that was used for training, and we combined them all together and then retrained a new model based on all of this data combined, and then saw how well it performed in New Hampshire. And so this box and whisker plot here summarizes the distribution of the mean absolute percentage error, and so I want to keep moving with the presentation, but just to quickly explain our thinking, we quickly eliminated the Florida-only model and then had to choose between the other 3, and based on both the median performance summarized in the table and also the interquartile range and the distance between the whiskers, we ended up selecting this extended model to continue, or basically to use for our New Hampshire analysis. So based on this model, we went through and estimated volumes and then compared them to the actual volumes in the same way I described previously, and we generated these error metrics, both overall and then separated by different scenario, by road class, volume level, average number of probe counts, and the results were remarkably similar to what we had seen in Florida. Again, we then, after training and evaluating this model and becoming satisfied with its performance, then expanded this to the entire, statewide TMC network. So if you look at this animation, we can then light up this whole network, and we've obtained hourly estimates, every hour of the day, every day over the course of these 3 months, everywhere on the network. Again, like I described in Florida as well, we repeated this AADT estimation process where we rolled up these hourly estimates to the AADT level and then quantified the model performance. Again, the accuracy level is very high, which is encouraging, and it again indicates that this is a viable way to estimate annual average daily traffic. So one more thing I want to point out, as I wrap up here, this final experiment we did was to we settled on this extended model, which combines Florida and New Hampshire data, and in doing so, we initially used all of both data sets. One thing we wondered, though, is whether we really needed to use all of both data sets. So to test this, we took the entire Florida data set and then trained new models with just 2 weeks of the New Hampshire data set, 4 weeks, 6 weeks, 8 weeks, etc., until we used the entire data set. And what we found is that the model performance doesn't change very much. It changes when you first introduce the New Hampshire data. You do need to introduce some of it, but once, with only 2 weeks of the New Hampshire data, the model predictions are quite good. So this has, again, the whole, I think, takeaway that I want to communicate for this idea of transfer learning is that, particularly for small states, or as we, hopefully expand this process to new locations, if we develop a few really high-quality data sets with good high-fidelity continuous count data and can generate these high-quality volume estimation models, we can leverage that information and take it to new locations to help improve the performance of volume estimation models in new locations, particularly in ones where it's hard to acquire a lot of data, possibly because it's a small state. So overall, just to summarize, we've mostly wrapped up this Florida and New Hampshire analysis. Again, we've initially focused on the hourly volume estimates. This is the core part of the process, and then there are different flavors of that, such as focusing only on freight volumes, taking those hourly estimates and rolling them up to the AADT level. So there's some different variations and use cases of this approach. Again, in the future, as data becomes available closer to real time, we're interested in the potential operational applications of this as well. And then we have the final takeaway that, which is really exciting, in that we can leverage some of these larger data sets that we've already looked at to help improve model development in locations where we have less data. And then I have a little bit of, I just have one more slide here with contact information with the three of us who have been primarily working on this from University of Maryland. And with that, I'll turn it back to Stan, who's going to share about the results they've been getting recently from NREL.
Okay. Well, I'm going to pause here a minute, Zach, because I saw a question come in while you were doing the presentation. I don't know if you can read that or not. I'll repeat it for everyone. It's from Keith Miller. The question, more or less, is there any understanding that this particular data set, I think the penetration rate was around 2%. Are there any concerns related to, is that 2%, representative of the whole, statistically representative of all the vehicles out there, or is that an issue moving forward? Do you think you could address that quickly? Put you on the spot.
Yeah, just a second. Let me read this for a second. This is Keith's question, right?
Right.
Yeah. So talking about the penetration rate, the question asks whether there's any important biases in the sample. I mean, I think if we were to go back and look, or if I think these slides will be available, there is a pie chart that shows the distribution of the probe data, and so for the particular data set that we're using, it does tend to have more trucks. But that said, so more trucks than passenger vehicles. That definitely constitutes a higher percentage of this key input data. But that said, our models are capable of adjusting for this, and they have, our target or our output of the model is the actual vehicles, being counted by the continuous count stations, and so that may be a different distribution of vehicles, but nonetheless the model can learn the pattern between these inputs and the outputs, which may be a different distribution of vehicles.
There's a follow-on question there about did this analysis between Florida and New Hampshire, what about the drastic weather and terrain differences? Could you remind us what the date range is on these data sets? Did it include winter weather or not? Or is that something that remains to be investigated?
Yeah, so the New Hampshire data set was Q3 of 2017, while the Florida was Q4 of 2016. So we did get the end of the year. The thing I would say regarding the weather, yes, there are certainly some differences between the two, and I think that's why we see when we try to take the Florida model and apply it directly to New Hampshire, there are some problems. But in general, I think the main idea is that this Florida model is able to learn many of the important patterns between speeds and probe counts and weather and everything. And so yes, during different times of the year, there are going to be different weather conditions in both states, but we are taking weather into account as a model input. So, precipitation, presence of precipitation, and temperature and various things like that. So yes, in Florida, perhaps some of the weather conditions wouldn't have been seen that were in New Hampshire, but we still are using the New Hampshire data to as part of the training process. Additionally, some of the
Zach, this is Denise Markow. I happen to live in New Hampshire, and I also know that one of the reasons that we chose the Q3 data set, which was the core of the summer months, was that that type of data set could closely, not necessarily be the same, but be closer to a Q4 Florida data set, and that weather would not be necessarily an issue at that point in time. I don't know if that's helpful to you, but I do know that was a discussion we had.
Yeah, and I think another thing to point out, this is a very fair question, and this is something that you're going to have challenges with when you're looking at a few months out of a year. So really, I mean, this question is well received. In order to have ideal model performance, you'd really want to have a full year of data. I mean, we're working with what we've been able to acquire, but certainly this this idea of seasonality, even if it didn't play a case particularly in this specific example, certainly could, and so we would want eventually to get at least one data set from an entire year where you are seeing different seasons.
Thank you, Zach. That's a good transition. I call all the work we've done up to this point proof of concept, and it shows the promise that it could be done. I think the next stage is prototype, and the big difference is I think both of our teams were working with like 3 to 4 months of data, and we realized we need a full 12 months, a full year, the full seasonal cycle to see if there's any hidden issues with those seasonal effects. I saw there was another question, and Justin handled that. Thank you, Justin. I'm going to move on now and share some insights that we've had from our air analysis here at NREL. And first want to thank the contributors there. Yehu I believe is on the line, and Vanu Garikapate. We haven't blazed new trails into new data sets. What we've done is gone back and taken a look at the air distributions and some of the other issues and see if we can gain further insights. And I was hoping to share some of those towards the end of this presentation. We have 3 topics. One is applying what we call a symmetric mean absolute percentage error. We looked at training bounds and some data filtering issues, and last on some performance during unusual events. First, I want to start with what we call the symmetric mean absolute percentage error, or as we call it, the SMAPE, not the greatest acronym in the world. Previous webinars, we shared that once you get down to low volume roads, one of the issues with the mean absolute percentage error is that the air gets inflated, particularly when volumes fall below 100 down to 50, 20, things like that. And that's mainly, if you can see the equation at the lower part, the volume's in the denominator, and as this falls, if there's any air at all, it gets extremely amplified. In literature, there's a way to address this. This is not a problem that's by any means unique to volumes. There's a lot of areas where this approach to the mean absolute percentage error has the same issues, and one way around it is what they call the symmetric calculation of it. And in the denominator, what they do is they average the ground truth with the estimate and divide by 2. And basically, it brings some stability to the measure so that when you look at aggregate scores, it's not dominated by the performance at extremely low volumes. In essence, this formulation of this symmetric MAPE caps the error between 0 and 200%. If we didn't do that, we could get some theoretical errors. It can literally go to infinity in theory, but they go incredibly high, and then when you average that in with the whole data set, it tends to dominate. We have implemented that, and we put it in some of our results. These were for the Colorado freeways. We put this symmetric MAPE column in right next to the mean absolute percentage error, and then you can take a look at the 3 different models we tested, and in each case, the symmetric MAPE is slightly less, and where this impact gets in is when we get into some observed very low volumes, it tends to cap it. The next slide shows it a little bit better. This is on the Colorado off-freeways, and once you get to off-freeways, you can get into some extremely low volumes. And recall that we showed you this slide, I think it was 2 presentations ago, when we took a look at the model results from machine learning, which is this XGBoost. We were getting MAPEs of 50.6%, and if we compared it to a linear model, 314, if we compared it to an AADT-based model, 161. And then if you were to take a look within the symmetric MAPE formulation, there's still the errors are larger than on the freeway, but they are down within reasonable comparison ranges. And if we were to show this in contrast, recall this was with the results filtered for only 20 vehicles per hour and above. And the MAPE formulation was 29.7, compare that to 50.6. So the big difference between this column of numbers and this column of numbers right here was the inclusion of extremely low volumes, these 20 vehicles per hour or lower. So then when we formulate it with the symmetric MAPE, you'll notice this column here compares pretty much on par, slightly less with this symmetric MAPE. The main point being that with the symmetric MAPE, when you produce overall aggregate estimates of performance, they're not dominated by those samples in which the vehicles of absolute volume starts to approach 0. All that said, from this point out, when we present the results, we'll be using this symmetric mean absolute percentage error formulation just due to its stability properties. The next thing I'd like to talk about is some of the issues related to training bounds and data filtering. The fundamental question there is we were seeing some large errors at high volumes that we weren't expecting, and we were wondering if this was due to the lack of appropriate training data. This is what illustrates it best. If you take a look at the Colorado data set, the mean absolute percentage error is a function of absolute volume. You'll notice that it decreases continuously up until about 5,000 vehicles per hour, and then after 5,000 vehicles per hour, it starts going up and can get quite large. And that made us scratch our head. Do realize that at 5,000 vehicles per hour was kind of a break point. We only had a small amount of data, a tail of the data that was 5,000 vehicles per hour or greater, as shown in this histogram at the bottom. This next chart kind of shows what our expectation would be statistically. We run a few of these results just on theoretical data sets, And as your absolute volume increases, if you just take a look at the sampling theory, you would expect this error to continue to decrease. And what caught our attention is even though we have a small amount of data around here, that the errors tend to escalate. And our guess at what was going on is that there was not sufficient training data once we got above 5,000 vehicles per hour, on up to about 10,000, I think was the greatest here, to train the model and make it stable. We were able to verify that. I got a couple slides that show that. This next, we color-coded the residual plot. On the left is the residual plot versus absolute volume or ground truth, and on the right is the residual plot versus probe count. And on the left, if you take a look at where these residuals are, the color coding is all from one segment whose volume is almost a magnitude order larger than all the other freeways. It's a section of I-25 near the downtown of Denver. It has more lanes, and all that volume data from 5,000 vehicles and above comes from that roadway, and then we color code it, and we can see these large residuals all come from that one segment. And if you take a look at it, the probe count, you can see it here as well. This confirms, recall the cross-validation technique, when that one particular segment was not in the training set, this resulted in all these residuals. So it confirmed our suspicion of what was going on. We're taking that information and using it to enhance the model approach. One thing we didn't anticipate seeing, and this will be in the next slide, if you can see some of the color coding right here at 0, this caught our attention as well. Unfortunately, the color coding is lost on these next two slides, but it's the two issues that we're moving forward dealing with. The first is this out-of-bounds training. We have ways to approach this. We're already formulating it so that when we get together next time, we're seeing if we can take this data, we can initially flag it, and then once we flag it, compensate in the model, more or less allow it to do a better job extrapolating if it need be. It also gets into the issues that University of Maryland was looking into with some cross-training. If we bring other training data sets, something else that has some training data at these extremely large volumes to make sure we don't violate some of the bounding issues. The other issue that we were looking at, again, are these data issues of 0 reported probes. That made us kind of go back and take a look at our data sets. This next one kind of shows what's going on. You put this plot together. There's two data traces here. One is the ground truth volume data coming from the continuous count stations for about 6 days. And notice these 2 days in the middle. If you take a look at the probe count reported through our data feed, it flatlined, meaning it went to 0. It reported 0, which we're learning is an indication that data line went off service. I was trying to show another plot here. The actual prediction didn't flatline. The actual prediction attempted to predict something similar to what was ground truth, because the machine learning learned that when it flatlines that it's no longer valid data. But this is something that we're going back to the data input on. We're going to create flags for when it flatlines or when 0 is reported, and understand better and perhaps push higher fidelity out of it. But at a minimum, put up a flag saying that if we ever get 0 probe input, or in this case flatlines, in this case put up a flag that the algorithm is then reverting to other input in order to estimate volume.
Did you know that TTI operates a full-service proving ground facility where we can...
We're getting bleed through on the conference call. If you could mute out, please, get some advertisement in the background. I wouldn't mind that if they actually paid advertising fees. Last thing we had, short, is performance during unusual events. This is related to University of Maryland's work, in which they took a look and flagged, hey, you're 1, 2, 3 standard deviations away. We took it a step further and say, can we take a look and estimate how well the system performs when unusual events happen? And our first attempt at this, this chart describes what happened. We separated the data and we looked at it by location, by hour of the day. And for each location and for each hour of the day, we divided up all the data points into the lower 5 percentile, the mid 5 to 50th, the 50th to 95th, and the 95th. And into these percentile ranges, you can think of that lower 5% are the unusual days of extremely low volume, and the upper 95th to 100% are the hours of the day where it's extremely high volume, or our unusual events. And then we went through and calculated our error measures. If you take a look at this, this directly results from the previous segregation of data. If you look at the 0 to 5% in the MAPE range, and we also brought along the symmetric MAPE, looking at the mean absolute error and looking at the error to capacity ratios, we were pleased to see that these MAPE calculations were consistent. We did perform better in the in-chart range between 5 and 95% with a symmetric MAPE of 16 to 17. But even on the unusual days, the 0 to 5 and 95 to 100, the symmetric MAPE only approached about 20%. So even in extremely unusual circumstances, the error measures did not go unstable. Then if you look at the error to theoretical capacity, which really makes sense at this 95 to 100%, we're at about 6.4. We like this approach so much, we took it a step further. We're saying, similar to University of Maryland, let's divide the data up into sigma ranges, or the standard deviation ranges. So we did the same thing for each segment. For each hour of the day, we divided up all the ground truth data into standard deviation ranges. On the positive side, 0 to 1, 1 to 2, 2 to 3, and 3 to 4, and then on the negative side, the opposite way. And then we calculated error measures. And this kind of gives you taking it from the statistical realm into what this actually means. If you're looking at plus or minus 1 standard deviation, this is your regular traffic without any major perturbations, things like that. If you're looking at the range of 1 to 2 standard deviations, you might have a minor incident or common weather event in your area. If you're looking to 2 to 3 standard deviations or sigmas, you're talking about possibly a fatal accident, some type of special event, a big game in the area, possibly a snowstorm. And then your 3 sigma events, these are very unusual, very rare events, maybe a blizzard, maybe an eclipse like we experienced throughout the U.S., or possibly a hurricane. So this kind of gives you the percentile ranges. And then we took a look at the errors. And similarly, if I turn to here and take a look at these sigma events and take a look at the symmetric MAPE column as far as the mean absolute percentage errors, it's not until you get to the 3 sigma events right on the very edge that the symmetric MAPE kind of budges from the 16 to 18% range until these 3 sigma events that they're still in the 24 to 25% range. And note that 3 sigma events in the data were only 1/10 of 1% of the time. We can also report it as the error to capacity ratio, and we see a similar pattern there. Unfortunately, we can't report it as R squareds because R squareds reported on the entire data set. At least we haven't figured out the formulation to think about it there. But within these other error metrics, we like this segregation of data into this standard deviation range or the sigma event range, and then taking a look at how well it performs versus how unusual the event is. Okay, that is summarizing what we did. We implemented this symmetric mean absolute percentage error. We're digging into the error analysis, kind of honing in, zeroing in on some of the issues there, and some of the flatlining kind of surprised us, but we're tackling that as well. Ultimately, we're working towards both improved models, which we think if we take those into account, we can push the performance metrics up even another notch. But we're also working towards confidence flags or a confidence number, possibly a variance, and identifying information importance, similar in concept to the first step that University of Maryland did in their work that was presented. I'm looking at the input. I see Stephen's commenting that there may be issues there at large volumes just from continuous count stations and some of the known issues there. Very much would like to carry on that conversation, Stephen, as well as we dig into some of these issues. I paused and Stephen also had a comment about unusual events and the errors around that. And yes, I'd like to take it up and take a look at that document that FHWA when they investigated it as well. All right, this comes to the end of our technical presentation. I got a couple slides left that's more programmatic in nature, where we're at in this research program, what to expect in the near future. I'll pause here as well if anybody wants to jump online, unmute their mic and make a comment or have a question. Now's a good time to do so. I'll go ahead and cue up the next slide while we pause.
Stan,
Yes?
there's another question in the chat box from James Lee.
Okay. James asked, it seems that the normal distribution is used for all time periods. I was wondering the assumption behind. Can you shade some light on it? I like that question. We have internal debates. I mean, researchers like to keep each other honest, and that's one reason I'm so I've really enjoyed working with two teams, University of Maryland and NREL. Friendly competition, we want to do the best we can, and we look over each other's shoulders, keep each other honest. And one of these, we're asking, we use some of the assumptions of a Gaussian distribution or assumptions of normal distribution to divide up the data. How valid is that? We've had discussions internally, should we use some robust statistical techniques which are more percentile based to identify these unusual events? Or should we just fall back to some of the more standard deviation calculations? We are aware of that. We've chosen to stay within the Gaussian distribution assumptions. Probably more, it's straightforward, well accepted, but also double checking it periodically to see if we're not, tripping on some assumptions of distribution problems. James, we can discuss that offline. I'd like for you guys. This is the steering committee. With the steering committee, we share at a much more granular level than we do anybody else, and we also make the results available to people so that if they want to do their own testing or take a look at the residuals within a certain perspective, we very much welcome that. It's always on these discourses that we get new ideas or we get, hey, another error metric to watch. So I hope that addresses your concern there, James, and we'd like to talk to you offline about that as well. I see, Stephen, you can't jump on the phone because of the cube farm issue. Understand that. Here's a few words, kind of where we're at with the R&D program. I say we're in the home stretch. We anticipate closeout of this funded effort by end of 2018. We actually anticipated it by about this time, but we had a small injection of additional research funding, which is going to extend the effort maybe another quarter. With that small injection of funding, NREL and UMD, we're going to continue on metric work, error analysis, and confidence. We think this is important. We think the proof of concept has been accomplished, but in order to set us up to apply it in the field, we need to go into that next effort with more of these issues related to the tails of the distribution, well quantified with our error metrics as solid as they can be. NREL is going to also take an additional step. We're going to analyze another geographic area within the coalition. We haven't decided on which area that is. It's probably going to be a region. We could do a small state, or we could do a metropolitan area, but not a large state by any means. And we're working to see which one would provide the most benefit to the research program or the most benefit playing this forward. University of Maryland is likewise going to continue working, looking on their truck estimation, which shows promise, as well as some vehicle type analysis. So when we get together again in 3 or 4 months, it's not been scheduled to expect additional technical detail along these lines. Kind of backing up a little bit on where are we at in the grand scheme of things. The Vehicle Probe project has been going on for about a decade or more now. The original Vehicle Probe project that was originally went out for bid, we had a single vendor and we were bringing in speeds and travel times. At the time, it was a high risk, high reward. We married it with a good validation program that continues to this day and showed the value in this. 3 or 4 years later, we created Vehicle Probe version 2 when we went out for bid. We created a marketplace. Again, it would emphasize travel time and speeds, but we began to realize That probe data could bring in other value-added tools. In addition to going to multi-vendor, we began to bring in ancillary products, things like needed maps, trace data, and other products that the vendors could offer that either added value or complemented their base data of travel time and speeds. Well, we're getting ready for what I call version 3 of this, meaning the contracts will probably expire in 18 to 24 months and we'll need to go out to bid. And in version 3 of it, we anticipate everything that we did in Vehicle Probe 2, but then also be prepared to include the volume estimate work. That's why we're collaborating with vendors now, anticipating, hoping to get first adopters in the next year or two, but by the time we got Vehicle Probe 3, it'll be mainstream enough that we can include it in the bid specs. And there's other emerging capabilities out there, which are the topics of many other webinars, origin and destination, what we call trip or trace data, and there's many things that can be done with that. We're keeping an eye on that as well, but really targeting to see if we can get these volume estimates as part of the next iteration of the Vehicle Probe project. With that in mind, one of the major outputs that we're pushing towards is recommended specs for volume estimates, and you'll see that as a major project deliverable ultimately. Moving forward, what I call from the lab to the streets, when we had our national webinar about 3 months ago, we said, hey, we think we've sufficiently demonstrated proof of concepts to learn more and develop this more. We actually have to do initial prototype implementation. Several of you have stepped forward. I listed all the states I'm aware of. There may be others that we've had individual one-on-one discussions that they came, and this discussion is, this looks promising. We have an application we think this could drive. How do we get to the next step? Possibly do a prototype deployment in a specific area or for a specific reason. The other good news on this is the vendors are also responding in turn and collaborating. They're creating either custom data packages or services to support these volume estimates moving forward in a prototype manner. We have yet to define exactly what the next step with any one of these partners will be, but those discussions are ongoing. So if you're interested, please contact Denise, myself, or Kaveh. Also be aware the US DOT through FHWA is a pooled fund study in motion. It has, I think they're still at the stage of recruiting states and packaging up. But it's focused on new sources of volume data to support the highway performance monitoring system. And if Stephen had a mic that he could talk, I'd turn it over to him to let us know where it's at. But Stephen, if you can update the group, that's more than welcome. I know I touch base with you about every month to see where that's going. I see you're typing now, so maybe you'll have an update for us before the end of the webinar. With that, I'll turn it back over to you, Denise. I think we're through with all our technical and all our programmatic updates. I'd like to entertain final questions or discussion. As I said, comments and input from the steering committee, which tends to be a group that's very well learned in this area, and in the past you've provided us many great comments we can act upon, and I hope that continues. Denise?
Thanks, Dan. Sure. I would say anybody who has interest in contributing or saying anything, you can turn off your mute and actually have a discussion. If there's something that you want to ask Stan or Zach relative to the work they're doing. I know that we're trying to move forward with a phase 2 and looking at different types of funding to be able to bring this to an operational state. But I guess I'm looking for some feedback from you guys in terms of what are you thinking relative to the project? Is there anybody out there that would like to give me some thoughts on that? Good, bad, or ugly? How about Stephanie? Stephanie, are you out there? From Port Authority? Stephanie? No? Okay. Anybody else and their thoughts? Oh, that looks like everybody's typing instead of talking. Okay.
Stephen Jesberger announced that the official, I'm not sure what PS stands for, but has now been designated, pooled fund. It is, if I can read this right, the 5384 official memo has been issued. We will be receiving funds from those involved soon. For details to to join, please let Stephen know. So thanks for that update, Stephen.
Oh, and Stephanie's good. No questions on her end. Thank you, Stephen. Yep. Looks like Keith Miller is typing too. Okay. Stan, there's a question from Keith in the box.
Keith Miller, understand that you can correct for oversampling of trucks, but I think it would be important to check for other sampling biases that may not be in the count database. For example, are income classes represented accurately? What about short versus long trips? Keith, let's pick that up and let's see if we can design into any of these analysis that we're doing on the air that may reflect some of that. I know a lot of the data that we're getting from these vendors comes in without attributes associated. We can make inferences on if they're oversampling the truck distribution or if they're oversampling a certain socioeconomic category, but we really don't have the data to back it up, and we're always searching for ways to analyze what could be possible impacts. So I appreciate that, and any ideas that we could follow up offline are very much welcome.
Looks like we have more typing in the box, Dan.
Okay. Another note from Stephen Jessberger, a few information about the pooled fund study and the final statement of work will be posted to the website as they're available. Glad to see that moving forward.
So Stan, can you talk about the difference between the work you're doing relative to versus the pooled fund study?
I can comment on it, but I think we need to take a look at the statement of work. I know we've talked with the people there at FHWA, Stephen and the many people working there. Their interest in this technology was sparked when we were starting to get results from the I-95 Corridor Coalition. It was also sparked from other studies out there. Of note that I'm aware of is the Minnesota, where they looked at methods similar to what we're doing to try to get better information on low volume roads. It's very expensive to send out tube counts, and they know that the data that they have on low volume roads is not to the same level of confidence that they have on other facilities. So my understanding of the pooled fund studies is really, I'm not going to say laser focused, but well focused on some of the known deficiencies within the HPMS system, trying to get aggregate estimates of traffic volumes and on road classes for which it's either expensive or they know that the current practice is not up to the level that they wish it were. And there's the website. That's excellent. We can monitor that website and see when it comes out. That's the best summary I can give without having knowledge of any of the actual statement of work that the FHWA is preparing.
Okay. And can I ask one other question relative to Zach's presentation? And this came up when we were talking with New Hampshire. When you look at the slides, there's a high concentration of what's perceived to be truck volumes as part of the mix. And when you look at the penetration rate, you look at the trips, and the discussion was that the model learns to adapt to be able to accommodate for the fact that if the results are showing you 16% trucks when you know really there's only 4% trucks within the state, but the model knows how to adapt. Can you provide a little more information on that at all? How that works?
Yeah, I can try to do a little bit. Yeah, essentially, I talked both about truck volume estimation and overall traffic volume estimation, and in both cases, basically this model sits between the inputs and the outputs. If most people are probably familiar with like a simple linear regression model. In these models, it's really easy to understand the impact that each individual variable has on the output. It is it is a little bit more challenging to describe exactly how this process works when we're talking about a machine learning model, because the artificial neural network we're using is highly complex, and it involves a lot of parameters that are calibrated. But essentially, if we're looking at overall volumes that as our output, that has some mixture of trucks and vehicles of different weight classes, and that mixture probably changes on definitely changes on different road types and times of day. And so we provide as a model input. We don't just provide the probe counts. We provide the weight class associated with each probe, or basically the number of probe counts of each weight class as we get it from the vendor for our probe data, so that our model knows how many probes we're seeing from each of those probe classes, and it tries to learn the relation between that and either actual volumes or truck volumes, depending on what we set as the output.
Thanks, Zach.
Denise, I was going to add a couple more comments on that. First, Stephen Jesberger responded back on the objective of the pooled fund project is to develop and to deploy methods and approaches to obtain vehicle volume and classification data with passively collected data. Thank you, Stephen. We look forward to seeing the more information when it's released. Another comment on that is we had these slides earlier about here's the advantages and disadvantages of machine learning processes. One of the, whether you call it advantage or disadvantage, is they tend to be black boxes, and they self-compensate, and until you dive into the results, sometimes it's hard to get meaning. And one of those examples is I shared the flatlining of the input data. We only discovered that when we did some error analysis. The model actually compensated. The model actually learned that when it flatlined, don't trust the input probe count, use other factors. We were both surprised when we learned that the input count can flatline, and we were also equally surprised when we learned that the machine learning method had already taken that into account without our knowledge.
Thanks, Dan. That's great. Okay. Is there any other questions that anyone might have relative to the work that the group is doing within the chat box? Otherwise, I think, Justin, if you go to the end, I think we're almost, we're done pretty much. Stan, do you have anything else you'd like to add, or Zach? Here's our contact information is on the screen. And obviously Kaveh, who is not here, but you've got myself, Stan, or obviously Justin from KMJ. We will, the meeting has been recorded, and that will be provided. We'll send you all a link when it gets loaded onto the website. And
yeah, thanks everybody for joining. It's really encouraging when we have this many participants on a steering committee whose technical content is admittedly quite in depth. We are moving forward to try to say, let's do our first prototype. We're targeting, it looks like, zeroing in on a metro area for a full 12 months. If you have any comments on what needs to be included in that prototype as far as either technical content or scope, that's where we're putting most of our thought right now. So appreciate it.
Absolutely. All righty, so with that being said, thank you, Stan. Zach, great job. Justin, thank you very much. We're going to sign off and keep you posted on everything that's going on. Thanks, Dan.
Thanks.
All righty.
All right, bye.